lead this, or you want me to? You want to lead the discussion?
Sure, try.
Go for it. I'll just add on.
Awesome. Okay, so up here we were doing this task. We were creating more of these parabolas, not these parabolas, these functions. So what was our first step in order to figure this out? What were we doing? Yeah, so we were trying to find those roots. So I really like what this group here did. They created that line. I'm sorry, Mr. Kenny. I'm not sure exactly what.
No, you're good.
You want
I'm going to add on to it. So, yeah, they created that line. That's why. What is that going to help us do? Graph the cubic. Now, did we 100% know it was going to be cubic originally? Not quite. So I'll start you off and then you can continue from there because I think you have this next piece of it. What I would remind you is that we are dilating these functions, right? What do we mean by dilating? That's a what? Yes?
Translation. Wait.
Transformation. Originally, I need you all to remember, originally we had what type of function? Quadratic. That shape was a what? A parabola, right? So we originally had a quadratic. That shape was a parabola, and then we are transforming it. We're dilating it by x minus 2, which is a line. Remember, we're using those factors, the graph of those factors, to help us graph the dilated function. And I think that's where you were focusing. So remember, we have a quadratic. We dilated it by a linear, so I needed the graphs of the factors to be able to get the graph of the final function. Continue off of that to how we get those actual values.
Yeah, so looks like, from here, what did we do in order to find that final function? What did we notice? So I see that this group has those dotted lines there. I know I was talking about with the 9s here that we were finding these, looking at these certain ranges. And then what do we notice about how we can create that resulting function? What did we do? What was that? Yeah, we're trying to find positive and negatives. We're trying to look at those corresponding outputs, those y values of each of our factors. Remember that with these dilations, we are literally multiplying. We are making sure that we are taking these values and they're multiplying together, each and every point there. So therefore, we know that all of these values, we can see that our linear function was negative this whole time. Our quadratic, our parabola, was positive this whole time. So we know that positive times a negative created a negative area. We knew that everything down here is negative, but we always know that these zeros, these roots, are important. We always want to make sure we're crossing those roots, so we know that we need to make sure it's approaching that. Now, what can we see about this area in between here? What did we notice about the parabola? What do we notice about the line?
Negative times a negative.
Yeah, we got negative times a negative. Negatives down here, negative times negative created a positive. So we know that we would be above that x-axis, we know it would be positive, but we have to come back down to our next zero. So from here, what can we tell from here?
Can we have all 11th graders who did not take their picture in September, please report to the theater? All 11th graders who didn't take their picture in September, please report to the theater.
What can we tell about the values to the right of this zero, of 2? Positive times positive, so we know it came out of positive. Now, I know I was talking to people here that some people said, oh, it bounces automatically. Some people knew it just bounced right away. So we can see that it's kind of bouncing here as well. Why do we know that it was going to bounce right away? We have a double root.
And if I could, I was just going to add in, I just want to point this out, because this was what I saw over here with this group to start, right? And when I came over and I started asking about this, what I want to emphasize and point out is the original pink graph was what type of function? Quadratic, right? Y equals ax squared plus bx plus c. So how many zeros does that have? We'll go with 2 zeros. What tells us it has 2 zeros? Not just the exponent. The degree, there's something else with that. A 3-word thing. Actually, technically 4 words. fundamental theorem of algebra, right? It's not just the degree. We have to include that detail of that fundamental theorem of algebra. It's second degree, so it has to have 2 roots. But remember, we're transforming it. We're multiplying it by a linear, which has how many zeros? Why did I put a C there? It has 1 0, right? So how many zeros should we now have? We should have 3. Guys, if you draw a parabola, though, does that have 3 zeros? A parabola, by definition, is a quadratic function with 2 zeros. And he has to keep that in mind. And so, notice, Mr. Javi, continue with that idea of that double root there. Well, you were talking about the double root, so it has how many zeros there?
Yeah, double root, how many zeros are there? 2. Notice how over here, we cross through that x-axis, right? How many roots do we have here? We had just the 1 root, right? So can we say we have 2 roots here, 1 root here? How many roots do we have total? 3. What is the degree of the polynomial again?
The dilated one. Yeah, no, just wanted to clarify. Dilated,
Yeah.
the final function has how many roots? 3.
3.
Yeah.
All matches up. That's a good way to double check yourself in the future. You can ask yourself, hey, you can use the fundamental theorem of algebra that we were saying. Does my degree match the number of roots I have? Am I making sure that those double roots are bouncing and the single roots are crossing, etc.? Yeah.
We good with that? So I know some of us were freaking out earlier when we looked at it. And I was like, Mr. Kinney, I got no clue what to do. Literally, we did this as a bell ringer yesterday. It was on that sheet of paper that I gave y'all. Don't forget to use your resources. But I want to go ahead and tell you on the demonstrated understanding today, there's a question or two where I'm just going to go ahead and give you the factors and ask you to sketch what the function would look like if you were to dilate or multiply those functions. There's going to be 1 or 2. I just say 1 or 2 because I know there's a total of 3 and I don't remember which one I did 1 of and which one I did 2 of. But there's going to be at least one where I give you one function and I say, hey, dilate it by this other function. So what are you going to have to do before you can start to do that dilation? Well, so like here, I asked you to dilate by x minus 2. Did you already have that x minus 2? No. So what did you have to do first? You had to, well, you could graph, right? Like, so remember, we're not just sketching this line here. We're graphing that factor. And then we're sketching off of that. Do notice the difference between graph and sketch. Graph is when we are super accurate. You were asking earlier, Drake, am I going to count off if you get the heights wrong here? Have I ever assessed you so far in our conversations about how tall it is? No. Now, I will say this. If you want to find a point and make sure you find out what the actual height is of that point and show it, that might get you to a CCC+, but like that's going extra above and beyond, right? But it's simply, again, like we've been talking about, I'm just estimating. I think this is the point 1, negative 1. And I'm going to estimate this point right here to be 1 comma, can we tell up there? What 1 comma, 1 comma negative 3. So like if we're literally multiplying those y values, what's negative 1 times negative 3? Positive 3, which a negative times a negative is a positive. So if you wanted extra accuracy, if you wanted that extra level of accuracy to get it, that would be more accurate. But is that the focus? The focus is just on the shape. It's on the positives and the negatives and the zeros. That's it. What are your questions before we continue? Going once, going twice. Sold. So remember, to dilate these functions, to sketch the dilated function, you got to have the graph of all those zeros. What do I have first on the docket? Okay, so I will say this. I'm going to be nice. We're going to go back to painted cube in a second. Let's go ahead and knock out the demonstrate your understanding so there's no break between, because the painted cube's not going to help you with the demonstrate understanding. So let's go ahead and see. Let's do the demonstrated understanding to start, and then we will do painted cube after that. Mr. Hobby, if you want to work through this while they're working. That's fine. It's a good one.
I'm not talking to you. I wasn't talking to you.
If you You were, I had been before, so okay. Join this meeting. Yes, ma'am.
I think you want some.
You don't need the calculator.
Probably pay for it.
My guess is one of my students in the left it there, let's just leave it so that hopefully they grab it. So I appreciate that. Alright, so while Mr. Hobby grabs those demonstrating understandings, painted cube yesterday. Kyron, thank you for volunteering your cube. So we started this, right? Remember, I wanted to extend this. No, you're good. I wanted to extend this idea to be able to find how many painted faces there's going to be on a cube when we get to a 7 by 7 by 7. I think I extended that to a 15 by 15 by 15. And eventually n by n by n. So meaning any sized cube that you could have. And so we got to this point yesterday, we're going to leave off on. And so I will say this, I would probably erase some of this just to ease our burden up in a second. But when we get to a 7 by 7 by 7 cube, how many painted faces, or how many faces, nope, how many cubes are going to have 3 painted faces?
I'll give it to my advisor.
How many cubes are going to have 3 painted faces? 8, 8, 8, 8, 8, 8, 8, etc. Right? Because what did we say this function was for the number of cubes with 3 painted faces? We said it was a... Ooh. Remember, it's staying the same, so it is a constant. And remember, it's not a constant rate of change, it's a constant... Not factor, because that would be some... What do we do with factors? We multiply them. It's a constant function. Remember, the entire function stays the same. No matter what size cube, y is going to equal what? 8, right? So the number of cubes with 3 painted faces is always 8. So when we have a 15 by 15 by 15, how many cubes are going to have 3 painted faces? 8. When I get to an n by n by n, how many cubes will have 3 painted faces? 8. That's it. We go with that idea? Comfy? Now, I want to talk about the 2 painted faces, because this is where we left off yesterday. What did we note about the 2 painted faces? It's what? Is it doubling? Is 0 times 2 12? So we need to be careful, right? There's this one case where it was doubling, but is that what it's always doing? It's adding by 12. So what type of function did we say this was going to be? We said this was going to be linear. Alright, so what I want to extend to y'all at this point is, before we continue with 1 painted face and 0 painted faces, if we know this is linear, what can I write? What could help me figure out what a 15 by 15 by 15 would look like instead of just continuing this table? Thing with an E? Say it again? Oh, could I write an equation that helps me get to the, I don't know, the 15th cube? Okay? So I want to extend that challenge to you. So quickly, let's work on writing this equation. Make sure we're talking about this with each other, because some of us struggled with writing the equation of linear functions. We need to build our understanding of this. Once we have that, we're going to come back together in a few minutes, and then we're going to talk about the 1 painted face and 0 painted faces, okay? So let's go ahead and find that equation. If you finish that before we bring everything back together, continue that table for 1 painted face, etc.
What's 3 times 12?
So let me pause. Thank you.
36 plus 8?
Thank you. If I can grab everyone's attention really quickly. Hey guys, y'all, we're forgetting a really important thing here. I need y'all to pay attention to this. All of us got the slope really, really, really well. Because what is a slope? Not just a rate of change. What type of rate of change? A constant additive rate of change. How do we mathematically show that constant and repeated addition? Multiplication. So if I could scoot by really quickly. So we already talked about this plus 12 yesterday, right? Constantly adding by 12, so 12x. But guys, what's the equation of a line? Y equals mx plus b. And there's several ways to get that b. And I will say there's other equations that we could use here. There's a point slope that probably would have been a little bit more helpful, but we just didn't have time to study that point slope. But guys, what's my input if I want my b? What's my y-intercept? What's the input for my y-intercept?
0.
It's 0. So we need case what to find that y-intercept? We need case 0, guys. If we want an input of 0, notice this is case 4, and I will point this out, I need y'all to note this, because I saw a lot of us just doing 12x, and that's fine, but note, what's 12 times 4? 12 times 4 is 48. Is that this 24 here? What's 5 times 12? 60. Is that this 36 here? No. So, guys, don't forget, we need a case 0. Can I walk my table back to get to that case 0? You have to have a y-intercept if you're doing that equation of a line. And I know I'm constantly adding by 12, so to go backwards, I've got negative 12 here, and then negative 24 for my case 0. Let's check this equation. What's 5 times 12? Okay. What's 60 minus 24? Does that input map to the correct output? Look at case 6. What's 12 times 6? 12 times 6? 72. Thank you. Anybody want to take a shot in the dark what 72 minus 24 might be? 48. 72 minus 20 is 52. 52 minus 4 is 48. So the correct input mapped to the correct output. So guys, we got to remember when writing these equations, we need to think through what is going to have my correct inputs mapped to my correct outputs. When I want a y-intercept, what's the input for my y-intercept? 0. There are other ways to do this, but that is the way I would focus on it. Thank you, Greg. All right. So how would I now find for case 7? What do I do with that equation? 12 times, well, 12 times whatever number, right? So for case 7, 12 times 7 minus 24 gives me an output of 60. How about for case 15? 12 times 15 minus 24, right? So that's the beauty of getting to that algebraic. Remember, the table is great for helping us find what? Patterns, rates of change. But that equation is great for helping us find things into the future. That's why I extended us into that 15 by 15. And now, what would it be for case n for any size cube? Yeah, that input is just now an n. Notice that creates an expression. That's literally the linear that you wrote, or that we wrote together. But guys, I need us to remember linear functions. Y equals mx plus b. Don't just find your slope, also find your y-intercept. There are other ways to do it that I'll explain a little bit later. But I now need us to move into one painted face. Be careful, this is not a 24. For case 5 at least. What do you think it is? Or for one painted face. How'd you get 54?
I got the, well, I counted the painted 3 faces in this one, and then I just added all of this together.
So you knew this was going to be 27?
No, yeah, because when I did the block, I pulled them all off.
Ah, so if I can see this real quick. Here's the 4x4. And so when we look at the 4x4, so that's this one right here, and you pull it apart, and I think that's what I did with y'all yesterday, or was it a different group? Different group. Okay, when you pull it apart, how many cubes do you have on the center that will not get any paint whatsoever? There's 4 here and 4 here, so there are 8, okay? So we do, oh no, I'm so sorry, I'm breaking your cube. So we get a total of 8 here. Oh my goodness, I'll fix it, I promise. Alright, so there's a total of 8 here. There's a total of 1 here on that 3 by 3. So how did you know it was going to be 27 here? Did y'all build a 5 by 5?
Yeah, we took it apart.
Oh, okay. So they built a 5 by 5 by 5. Got it. And on the inside, they had a total of 27 cubes. Anybody see any kind of pattern here that might help me get to a 6 by 6 by 6? Anybody recognize that set of numbers of 1, 8, 27?
It'd be a 4 by 4.
So on
3 by 3.
okay, so this is a 3 by 3 by 3. This is a
2 by 2.
so for the 0 painted faces, we're noticing that for a case 3, yeah, let's go to case 3. On the inside, it ended up just being a 1 by 1 by 1. Case 4, it's going to be a 2 by 2 by 2. Oh. So then it would just be 3 cubed. Now we'll point that out. That's for a case what? 5. So for a case 6, what's it going to be?
4 times 4. Yeah.
So I want you to think about that idea. So actually, let's figure out that 0 painted faces then, since y'all are already noticing that pattern. Let's try to figure it out for case 7, case 15, case N, and we'll come back to the 2 painted faces. So think about this pattern that they're noticing for those cases. Let's figure out what's happening with 0 painted faces, and we'll come back to 2 painted faces afterwards. All right, y'all ready?
What?
Or sorry, 1 painted face. That's the one we're missing, right? Yes. So 0 painted faces. Let's figure out what's happening for case 7, case 15, and case N.
How is that? Yeah, like a quadratic.
Additive, right? But not just any number, right? It's adding by the same
For
thing,
the zero.
right? What do we call that again? Yeah.
Well, he asked us like,
You're
how would you
saying-
find like,
Yeah, so the rate of change is a constant additive rate of change. Yeah, I would definitely make sure to know that. And then what did we call that again?
Thank you, Drake. Thank you, Leah. Thank you, Megan. Thank you, Mr. Javi. All right, guys. We only have about 4 minutes, and so I want to establish a couple things so that we can come back tomorrow. Sorry for mistiming things. If we had like 10 to 15 more minutes, we could finish this. But I need us to pay attention to something. A lot of us are recognizing, so once again, 3 painted faces. What type of function was this? Constant function. 2 painted faces was a linear function. Now, when we got to 0 painted faces, it took us a hot minute to get there, but we started to realize that we could do what to get the inside, the 0 painted faces? So we took our case number, subtracted 2 from it, and then what? Cubed it. Because on the inside, what do you have on the inside here? You have a smaller what? A smaller cube, right? So what do we do to it? We cube it, okay? So we're starting to notice, and so for case N, for the 0 painted faces, case N, what would the expression be?
N minus 2 cubed.
So N minus 2 cubed. All right? N minus 2 cubed. And so 0 painted faces is what type of function? N minus 2 cubed is what type of function? It's a cubic, right? Now, any predictions then? That 1 painted face might be a quadratic? Notice that's our prediction. Now, man, I really hate that we didn't get to quite finish that today. But what I do want to emphasize and I want to point out is, I've said this a little bit in the past, but I really want you to understand, math is the study of something. Actually, 2 words. It's blank and blank. Say again. Okay. What did the table help me find?
Study of algebra.
It is so it's not all algebra. There's a whole lot of math that's not algebra. What did we get to find in the table that we wouldn't necessarily see in other places? What? Patterns. Math at its core is the study of patterns and relationships. That's what math is. And so I just want to emphasize and point out, you're finding a pattern here to write this equation, right? To get the number of 0 painted faces, we just took the case number, we subtracted 2 from it, and then we cubed it. Every time. And that was found by looking at this pattern here, by looking at the fact that it was a 1 by 1 by 1, a 2 by 2 by 2, a 3 by 3 by 3. And so now we're starting to see this pattern that there's a constant function, there's a linear function, there's a quadratic, hopefully we'll see tomorrow. And then here at the end we have a cubic. And I told you all at the beginning of this painted cube task, what was the goal? To understand what better? So don't forget, this is why we do these things. What were we trying to understand a little bit better? A cubic. Remember, we've studied linear pretty heavily, haven't we? We've studied quadratic pretty heavily, haven't we? Now what do we need to understand? A cubic. And I mean, constant's pretty straightforward. So tomorrow, we're going to go deeper into the idea of a cubic. And we're going to look to see if there's a quadratic there. So once again, please take a picture of what we have, right? So we should have an equation for constant, we should have an equation for linear, we should have an equation for zero painted faces, that cubic, and we're going to start back there tomorrow. We will go over the demonstrate your understanding after we finish painted cube tomorrow. So be aware of that. Thank you all for a great lesson. I hope that it was at least challenging. It was a thinking, thought-provoking thing. Good. That's what I like to hear.